Okay, here we see the definition of kinetic energy, the definition being 1/2 mv squared. In the class notes, you see a bit more about where that definition comes from and what it means. Now, kinetic energy at an initial velocity v0 is 1/2 mv0 squared. Just by the definition, if the velocity is v0, then we're going to get 1/2 mv0 squared. What if we double the velocity? What if we change the velocity to 2v0? What's going to happen to the kinetic energy? Well, we're going to substitute 2v0 for v. We're going to get 1/2 m times the quantity 2v0 squared. Now, we have to square the whole 2v0, so we end up with 4v0 squared, and it should be clear that this expression is 4 times the value of this expression, that the ratio of this energy to this energy is 4 to 1. That when we double the velocity, no matter what our initial velocity is, we're going to have 4 times that velocity, or 4 times that kinetic energy. Okay? Now, kinetic energy of 5 kilograms, 5 kilogram object moving at 12 meters per second is what? 1/2 times 5 kilograms times 12 meters per second squared. That's 360 kilogram meter squared per second squared. Now, what's a kilogram meter squared per second squared? Where does that come from? Well, the meter squared per second squared comes from squaring the meter per second. The kilogram, of course, comes from the kilogram. Remember that a kilogram meter per second squared is a newton. So if we take a kilogram meter per second squared out of this expression, we're left with a meter. And over here we've got a newton, so we've got 360 newton meters, which is 360 joules. Okay, 360 joules of kinetic energy. If we double the velocity from 12 to 24 meters per second, then the kinetic energy is 1/2 times 5 kilograms times the square of 24 meters per second. And you can work that out. The numbers are fairly simple. We end up with 1,440 joules of kinetic energy. Okay, we note that 1,440 joules is 4 times the 360 joules that we got here, so that by doubling the velocity, we quadrupled the kinetic energy, as would be expected from this more general analysis here. And we note that the ratio of kinetic energies is 1440 over 360 equals 4. Just another way of saying that we have 4 times the kinetic energy here. Now let's do another example. This being a slightly more complex example, and I've written this out a little bit smaller, and we're going to zoom in on that just a little bit so we can read it a little better. Let's say that we have a 30 Newton net force acting on 12 kilograms for 8 seconds. What can we conclude from this information? Now, you really should pause the tape and see what you can conclude here. Well, one thing we can definitely conclude is that the acceleration is net force divided by the 12 kilogram mass, or 2.5 meters per second squared. So that comes out in a fairly straightforward manner if we simply remember how acceleration is related to force and mass. Then, with an acceleration of 2.5 meters per second squared, we're now on familiar ground. We have an 8-second time interval accelerating at 2.5 meters per second squared. That's going to give us a change in velocity of 2.5 meters per second squared times 8 seconds, or 20 meters per second. That implies a final velocity of v0 plus delta v. Now, it wasn't stated up here. You can see it here. We're assuming that the initial velocity is 0, so that the final velocity is going to just be the same as the change in velocity, or 20 meters per second, implying an average velocity of 10 meters per second and a displacement of average velocity times delta t, the 10 meters per second times the 8 seconds, or the 80 meters. The work done by the force, then, and our goal here was to maybe define delta S and VF in the work done, and maybe even the change in kinetic energy. The work The work done here is the product of F and delta S. Well, F is just our 30 Newton force that we started with, and delta S is our 80 meter displacement, so we have 2,400 joules. Now the kinetic energy, what's the change in kinetic energy? Well, originally we had velocity 0, so the kinetic energy was 0, so the change in kinetic energy is just going to be equal to half to the final kinetic energy, since we don't have the initial is 0. Okay, the 1/2 m times final velocity squared then is going to be 1/2 of 12 kilograms times the 20 meters per second quantity squared, or 2,400 joules. Note that the change in kinetic energy in this case is equal to the change to the work done, the change in the work amount. Okay? And that is, of course, what we said originally, that the change in kinetic energy is equal to the work done by the net force, and the 30 Newton force was our net force. Okay? Now, if we look at a diagram of our thinking of this problem, okay, we see that we were given delta T in the mass and the net force and the initial velocity. In this case, the initial velocity was 0, but it really doesn't matter that the initial velocity was 0. This diagram will work no matter what the initial velocity is. Okay, we have from the mass and the net force, we have the acceleration, which gives us our delta V when combined with the delta T. And then when we put the delta V together with the V naught, we get our final velocity by averaging the two. I'm sorry, we get the final velocity by adding the change in velocity to the initial. Saw that V average down there and got sidetracked, sorry. Okay, then the initial and final velocity are averaged to give us the average velocity, which is then put together with the delta T, the time interval, and multiplied to get the delta S. And at that point, we can say that the work done is F net times delta S. We've got the delta S and we've got the F net. We could actually draw the diagram. We could connect the F net and the delta S down here to get the delta W, but we'll just draw it here, or we'll just write it as an equation. And the kinetic energy is 1/2 mvf squared minus 1/2 mv naught squared. We've got the m and the vf and the v naught, so that we get those quantities. So that from this given information, we determine all these quantities as we saw, and we can come to the conclusion that the change in kinetic energy is equal to the delta W. Now, we did a special case where the initial velocity was 0, but if you work it through for any other initial velocity, you'll still find that the delta W equals the change in the kinetic energy. And I recommend that you try a different initial velocity. Try a 15 meter per second initial velocity with these conditions, and see what your final velocity and displacement and everything are, and verify for yourself that the delta KE and the delta W are identical.